Hello everybody and dear participants. A very good afternoon, good evening and good morning depending on the location where you are. It's great pleasure to welcome you today to our third webinar of 2016-17 with a very useful tool to facilitate in your day-to-day work area. Earlier from APQI platform, we have hosted webinars on various topics and many of you have benefited hopefully by attending those webinars. Asia Power Quality Initiative, in short APQI, is an independent platform that aims to build awareness and capacities on issues related to power quality. This pan-Asian platform, supported by national support network partners, continues to carry out activities towards capacity building and awareness amongst various stakeholders. We are working continuously to facilitate regulatory and standards initiative in respective countries. We provide a neutral platform for exchange of knowledge and best practices concerning power quality. Our website www.apqi.org is supported by Leonardo Energy Europe and is the single largest resource for varieties of discussion papers, research and data on power quality in all the countries that we work. We work with a focus on shared learning, transparent exchange of information and active engagement in this field. In increasingly digital world of today, the sensitivity of plants, process and equipment demand for high power quality environment, and poor power quality can impact severely both in terms of economics as well as safety. Transformers are one of the most important and high capex assets for electric utilities and industrial users. They are normally designed and built for use at rated frequency and perfect sinusoidal load current. However, with proliferation of nonlinear loads, transformers can no more be selected or evaluated on business as usual basis. The harmonic currents cause increase in winding losses, and the high frequency harmonic voltage may cause large core losses, leading to early fatigue of insulation, premature failure and reduction of the life of the transformer. Therefore, harmonic analysis with loss calculation plays a very vital role in transformers to reduce harmonics effect. The economic analysis of any new or transformation project is the fundamental step for any investment decision. This holds true when addressing the increasing power quality issues in industrial and electricity distribution networks and key assets like transformers. In simple words, loss calculation means when ordering or purchasing a transformer, certain acceptable levels of core and winding losses are agreed between the client and the manufacturer. Hence, when purchasing transformers, it is important to compare the cost of the losses over the entire lifetime of various scenarios considered. It is utmost important now that utilities and customers adopt and evaluate the financial aspect of life cycle cost before making the investment decision for transformer. And we from Copper Alliance and APQI network have brought this simple open access tool to facilitate working and decision making of stakeholders concerned. Keeping this background in mind, I welcome you all on behalf of APQI India to this webinar titled Assessing Transformer Loss in Harmonics High Environment. Our distinguished industry expert from DNV GL Energy Advisory will share his expertise and thoughts on utility of this tool. He has been the architect for developing this tool. He will also show us case studies on loss levels in transformers simulated in normal versus high harmonic environment. I take great honor in introducing Mr. Hulshorst. Mr. Hulshorst has more than 25 years of experience as project manager and line manager. He is specialized and experienced in design and dimensioning of power transformers and reactors. In several projects, he is responsible for the transformer or reactor design. He was involved in quality assurance and quality control, including design review and specification of transformers in several countries. He is an expert on testing, design review, and specifications of large power transformers, converter transformers, and distribution transformers. Mr. Hulshorst has gained extensive experience with power quality issues, for example, voltage dips and harmonics of transmission and distribution systems. He has been project manager for several projects for traction, heavy industry, and other grid companies to reduce PQ-related problems. He has done several projects for a Dutch DNB on asset management on metering equipment for electricity and gas sector. He has also managed several master planning projects while training the staff of DNVs on master planning. I sincerely hope that you will find great utility of this tool in our analysis and decision making on transformers. We from APQI are working to bring to you other such tools to help in effectively addressing PQ challenges. We look forward to your active participation and use of this tool with feedback for improvement as well. Please do participate in the survey on apqi.org. Please download the tool now or little later, and please do use this tool and give us the feedback. With that, I wish you all a very happy session of free exchange of information and learning, and thank you.
Good afternoon. My name is Walter Hulshorst. I'm already introduced by Mana. Thank you very much for your nice introduction. Walter Hulshorst, I'm within DNVGL, Legacy KEMA. Perhaps some of you don't know DNVGL, but might know KEMA. KEMA has been bought a while ago by DNVGL. I am happy to say to you that today I would like to discuss with you a nice transformer tool that we have made to show you what you can do in case you have a transformer which is loaded with heavy harmonic loading, and how to proceed with those transformer, how to keep in order the transformer, what to calculate with losses, what about CO2, but also things related to the money aspects, of course. The agenda for today, I will do a small introduction, then we will discuss some total cost of ownerships of transformers. We will show you the examples of losses in transformers. I think most of you probably will know it, but just to get a good understanding, a common understanding, I think it makes sense to show you a little bit on that. And after that, I will do a demonstration of the transformer tool that we have developed, which you can download on your, as already mentioned, and feel free to do it and use it as much as possible and provide us with feedback so we can update the tool in case it's needed. And also we will discuss some studies related to the tool we have done so far. As I'm already introduced, I will very briefly introduce myself. As you might see in the past, a very long time ago, I was a very small child and played with trains, electricity trains. Then I got used to electricity and went to a university, the Han University in the Netherlands, doing all kind of nice things related to electricity. I started my career with Smith Transformers in the Netherlands as a design engineer over there. While I've done that for several years, I joined the industry in the Netherlands, Parenco. They make newspaper, mill paper. And after that, I joined Kima, which is now Legacy DNV, which is now DNVGL. I'm today business. I'm still involved with a lot of things related to power quality with transformers, and I'm the head of section of a team that's doing all kinds of things related to power system plannings. And of course, power quality is one of the topics which we have to deal with. For today, the webinar, I think we will focus on some specific topics. There will be a discussion going on what kind of key challenges facing the industry and utilities when they purchase transformers. A discussion on the key parameters of the transformers for the loss calculations. I think that's necessary. And of course, a demonstration of the transformer tool. That's why you all were here. But let me start with a very easy introduction. I think it's mainly important when people buy cars, and I've given some examples of a car which was about a couple of years ago very often sold, a Toyota Prius and a Volkswagen Golf. Both have a price, and let's assume that you want to use that car for 10 years and you drive approximately 20,000 kilometers a year. If you only look at the investments cost, I think you all would agree, go for the Volkswagen Golf in case you are only looking at the prices for the investments. But I think you all know if you drive a car, you will have some additional cost. Both cars do have a fuel consumption. I've added them, 4.3 liters per 100 kilometer for the Toyota and 6.2 for the Volkswagen. And also there is a cost of fuel. So based on that, you can also calculate the assumption each year that you need how many liters of fuel to drive that car. In case you take that one also into account, then you will see that the purchase price of the car is not the only thing that you should look at. Also look at, for instance, in this case, on the fuel price. You will notice that the fuel price for the Toyota is much less compared to the Volkswagen. And if you count them together, I think the total price you would probably select, in this case, if you only look at the economics, the Toyota, because it's a little bit cheaper, 38,000 euros compared to the total price for the Volkswagen, which is 40,000. 1,000 euros. That could be the same for transformers. If you have two transformers and on the left side you see a very old one and on the right side you see a very new one. If you look at both transformers, of course, both transformers do have a kind of price and also some losses which they have. And in transformers we have two kind of losses. We have the no load losses and we have the load losses. Later on we will discuss them in more detail. Both of them have a price, and you can imagine that the transformer with a low losses normally has a higher investment price because you need more material in it and those kind of things. So in this case there is also the transformer on the right has a higher price compared to the price of the transformer on the left side, which has higher losses. But there also, let's assume that you want to use the transformer and use it for 10 years and it's 50% loaded. Then you need, of course, to know your electricity price. I assume about 8 euro cents per kilowatt hour. And then you can calculate the total effect, of course. If you want to look at both transformers and taking the loss of the transformers into account, you will see that within 10 years the other transformer on the right side is more as a lower price in total compared to the transformer on the left side. Basically, that's it what you have to do when you compare transformers. Very easy. Don't look only at the cost of the investment, but also look on the operational cost of transformers. And of course, all of you know that there is much more than only looking at the losses. You also have to maintain transformers and those kind of things. But in this presentation, we will look at the losses of the transformer and the price, and also some CO2 emission, how to calculate with those things. If we talk about transformers, I think all of you might know that we do have a lot of transformers within a grid. I've shown you a picture of this grid and you can immediately see that we do have step-up transformers, which are normally with the power plant. We also have some transmission and distribution transformers, and it could also be an auto transformer, whatever. Also within stations you have some transformers, and sometimes you also have specific transformers for HVDC, or perhaps also some transformers which you are using within traction, or perhaps for heavy industry. So we have a lot of transformers within in the grids, and also within the industrial customer complexes or residential. If you look at the transformer, what a transformer is, and I've added a picture of a huge transformer in this case, not a distribution but a huge one. There are some things which a transformer has. It must have a magnetic circuit in a transformer. Also, it has some winding and coils, and also some transformers do have tap changes. You will see that the transformer has a tank and also bushings and some cooling. If you look at the build-up of a three-phase transformer, and I would like to show you going from, oh sorry, go back, showing from the picture on the left side, where you will see the low core, which is a three-phase core, and also you will see that there is a low voltage winding on one core. On the next one, after a low voltage winding, normally they will have a kind of insulation separation, because on the outer side of the windings you will normally find the high voltage winding. If you look in the picture right next to it, you will also see that on the outside, and this is just a dry type transformer which I've shown, you will see that there was also some construction parts above the transformer to make sure that the windings are definitely concentrated to each other because of failures within the transformer, short circuit failures. And if you look on the above side, you will see that there is a yoke above it from the core, and also there you see some construction parts, and on the outside you will see an high voltage winding and a low voltage winding over there, which is around the core, one phase. If you look at the materials which are used in transformers, the magnetic circuit, normally they have transformer sheets which are made from iron, and there is also some construction parts around the core, which is iron or stainless steel or whatever. The windings and coils are often made of copper. They also contain a lot of paper due to insulations, and sometimes between some windings you will find some transformer board, also for insulation purpose. For insulation, normally for an oil transformer you will use transformer oil, of course, and for a dry type transformer you will have the air which is used as an insulation, and also of course the epoxy within the transformer which is used. And for the tank around the transformer you will often see that it's made of steel in case you have an oil transformer, and for the transformers which are really high power, very often some parts of it can be used as stainless steel. Of course the transformer has some bushings, and of course, where the outside of the transformer you will need some corrosion protection to make sure that in some areas you don't have corrosion within a certain limited time, and that could influence your transformer. If you look at the magnetic circuit, how it is made, and I've this kind of pictures which are the huge transformer, you will see that on the left upper side people are making the transformer, the core. They are very made of thin sheets which should be well make the total core. Sometimes you will see that people do it automatically, they have robots doing it, but for the larger transformer normally it's done manual. And in case you ask me why a transformer is in most cases expensive, it's mainly because you have a lot of material in it, but also it's a lot of labor force which is needed to manufacture transformer. On the right side above, now you will see the core which is already fixed, except you will see there is no yoke inside, so the upper yoke is not mentioned over there. That's because of the fact that you want to make the windings as well, and the windings should be placed around the core, of course, and then afterwards you can put in the yoke. If you look at the transformer sheets which are used, that's a kind of iron which they use, and you can use also, and that's the picture on the right side, a G-joint laser scratched. To reduce the losses, it's necessary that you pick up the right connection of the flux going, the right density of the flux, and sometimes to make sure that the connections are very good within a transformer and you get less load, they make a kind of step-lap pattern. So you have a good overlap between all the sheets which you have. And also another way is looking at a laser scratch material, and that's what you see over here. You'll see some nice forbs going in the vertical direction and over here in the horizontal direction. That's just to guide the flux within the transformer to make sure that the losses are as low as possible within this transformer. If you look at the magnetic circuit, the losses they have, basically there are some losses. I think most of you might know within those very small sheets you could have eddy currents. There you have your normal eddy currents which you can calculate very easily, and because there will be a current introduced within a sheet, and then you can calculate the losses. Also you can look at the laser treatment, and they can also have some losses, and also the G-joints where the transformers are the core is connected to each other. You can also have some additional losses. Another losses which you will find often in the magnetical circuit are of course the hysteresis losses, which you will get normally. I think everyone should know that or already knows that, and perhaps sometimes you can have some additional loss to the make of the core, how you do it, and also the kind of material which you are using. How to reduce the losses of the core? Well, basically, if you want to reduce your eddy currents, try to make use of sheets which are very thin. But do know if you make them too thin, it will be very labor extensive because you have to build it per core. Also use core plate of an excellent quality. You can use, of course, the first iron that you'll see, but it's better to have an iron which already has a laser scratch, those kind of things. That will reduce definitely the losses within the transformer. And also there is a methodology to make sure that you don't have an eddy current on a large sheet. Make use of paper insulations between, after stacking a while of sheets, make use of paper insulation between the core. Also effective interlacing methodology, we will show the G-joints already showed, and make use of low induction within the core. That's basically what you see in the picture over there. In this picture you will see on the horizontal axis the induction of the Tesla, and also on the vertical axis you will see the losses within a core. And there you will see that we have a different type of materials, M4, CGO, and still laser scratch, and you will see that the laser scratch material compared to the CGO has a lower loss almost at every rating of the Tesla. You will also see that the number mentioned over there, and that's the kind of the thickness of the sheet. So 30 means 0.3 millimeters, and 23 means 0.23 millimeters. So you will see that the lower, the thinner the sheets are, the lower the losses are, and you will also notice that in case you reduce the number of Tesla going from 1.8 to 1.2, you will see that also the losses will reduce. Also new type of transformers which are amorphous core, they can also be used. We do know that there is the maximum Tesla is a little bit less compared to the conventional transformers, but there you can see that they have a really low power loss. Next to the transformers, we also have some load loss, and basically the load losses that you have in the windings are Joule's losses, I squared R losses, or DC losses are they often called, but also we do have some extra additional losses. I don't know if you have ever bought a transformer, and if you look at the reports from the measurement from the testing, you will see that they do measurements for the losses, the load losses with the Joule losses, and also mention extra losses. And those extra losses, they are within the winding, and they are caused by eddy current losses. If you energize a transformer and also take a current into account, then you will have add a magnetical field between the windings, and that magnetical field, electromagnetic field, will have some impact on the losses within the windings, within the copper of the windings. Also, you will have some losses in construction parts that we already saw in the picture before, that there is a lot of construction parts in transformers. For instance, the tank and the yoke. If they are made of iron or another material, they can also have some losses, which are extra losses called. And also, and that's the aim of this presentation, you could have some extra losses which are caused by harmonics. Mainly the extra losses within transformers, they heavily depend on the frequency. For the eddy currents within windings, it's normally the square of the frequency, and if you talk about construction part in the transformers, you will often see that they are multiplied by 0.8 related to the frequency. The pictures below are showing just some transformers for a large transformer. You will see on the left side there is someone making a winding, and also in the middle you can see some cooling channels, and you will also see that there is a lot of paper used in this transformer to make it, and also some cooling channels below. And over here you will see the windings which are already fixed and can be used within the transformer. If you look at the material, the windings, how are they often made? They are often made of copper, and there you will see that you have some, for small transformers, they will usually use a single wire, but for if in case you have larger transformers with high currents, you will often use a CTC cable, which is a combined cable, where you will see that you have a small area of copper, but in total it's a large area. They are all in parallel. And that's a picture on the right side showing you how such a cable is made. And sometimes you will see that they are also with paper around it, and sometimes with some epoxy ice around it for insulation. If you look at what the eddy currents are doing within those, the magnetic field, I already told you about it, and also the harmonics, which produce a lot of things. You can imagine that the smaller the area is, the smaller the wires are, the less eddy currents you have. So it depends a little bit on the transformer manufacturer whether he is selecting the CTC continuous transpose cable or doing one wire. You will see that immediately when he uses CTC, the amount of extra losses within a transformer will reduce. If you look at the complete assembly of a transformer, this is a large transformer. You can see the guy standing on the right side. He's very small compared to this transformer. You will also see the windings on the outside. You will see the tap changer on the left side in this case. All the connections to that transformer, and you will see right in the middle there you will see this is the connection of the high voltage winding within the transformer. You will also see on the upper side, you will see all kind of construction departments to make sure that the windings are on the right spot in case they have a short circuit current flowing, that the transformer will not be have a failure during those kinds. So you'll see a lot of construction material within a transformer, and in this case it's made of iron. So you can imagine in case you have an electrical field that it also will have some currents within those construction departments. The tank, I already told you, that's also mainly made of iron or steel, and sometimes in some cases for very some transformers where you have some bushings going on, they will use stainless steel because that's a non-magnetical one, so it will also reduce your losses in case you have very high currents. Looking at the reducing the losses of transformers, I think, well, the material, the load loss I'm talking about, sorry, the material you can use is still copper, and don't use aluminium in case you have a large transformer, because you will have a larger transformer and it will also have a negative impact on your short circuit forces, because aluminium is not as strong as copper is. Also use a low current density in case you want to reduce your losses. I already told you use CTC cables, continuous transposed cables, because they will use your eddy currents in the windings, and also reduce the losses due to the magnetical field by using magnetical shielding. And that's what I show you on the picture. On the left side below, that's a kind of all thin magnetical sheets made of the same material as you use for the core, and they are on the right side. They are connected. You'll see them very often for large transformers. They are connected on the inside of the tank well, and it's only just to reduce also the eddy currents within your tank well. This is a very nice solution which you will very often see if you visit transformer manufacturers which making large transformers. Why an harmonic loading does have some bad impact? Well, in this case, it's a nice figure I show. You have a power transformer and you have some non-linear feeding like PCs, whatever. There will be a loading, of course, of the transformer, and due to the non-linear loads, you will have a higher current in the transformer due to all the harmonics you have. The influence of harmonics on the loading is that it will increase your current. It will also increase your load losses. If your current increase, then of course your DC loss or Joule losses will also increase because your current is higher. But also I already mentioned your extra losses will be very high because they are depending on the frequency. And if you have an harmonic, you have lots of frequency which you have to take into account. If your losses are higher, then you also will see that your temperature will be higher. You will have an increase of your temperature. And an increase of your temperature means a decrease of your lifetime of the transformer, or probably a failure of the transformer. And this is a picture, well, it's more than 10 years ago. It was a transformer which within the industry. You can see those are the windings which you have for several transformers up, and there you will see some cooling channels, and you will immediately address here over here that there was a kind of a flash over, and it was right in the middle over there, and also where this board was placed normally. We did an investigation on this transformer because it failed. It's obviously that this transformer has failed and could not be used within that industry. And then we found out that this transformer had a heavy harmonic loading profile, meaning that due to the harmonics and it reduces, it got more losses on specific places. Normally you will see the extra losses within a transformer are not evenly distributed within a winding, but they are mostly on top of the winding or below, on the below side of the winding. But on the top of the winding there is always the highest temperature, so it's mostly in case you have a harmonic problem, it will arise on the top of the winding somewhere. In this case it was the same. There was not sufficient cooling, and later on we found out that the specification within the transformer didn't mention that this transformer was going to use in a harmonic rich environmental. So that's something definitely in case you want to buy a transformer, and later on I will show you what will happen in case you don't order it. Make sure that in the specification you also mention to the manufacturer that has made the transformer in case it's used in an harmonic environmental area, because that's needed for him for the cooling, and also to make sure that he make the right choices to reduce the extra losses. That's very important. We see very often that someone is just ordering a transformer without giving those indications, and later on the transformer is used in a harmonic with lots of harmonic loading, and then it will definitely reduce your lifetime, or as you can see in this picture, damage your transformer, and then you have to order a new transformer, and that will take some time before you have a new transformer. What is happening in the transformer? In this case I will show you a picture in case you have an unloaded transformer at 50 Hertz. Normally you will have a no load situation, and for me it doesn't matter if the transformer is unloaded or loaded 100% or 100% loaded including harmonics in the current. If you add at a certain moment you are loading the transformer for 100%, you will see that you will have for the 100% loading without an harmonic, you will have the Joule losses within the transformer, the DC losses, and also additional losses, the extra losses. That's the same for the transformer which is loaded with harmonics, except we will also get some additional losses due to the harmonics, some extra losses. And if you count on it that you thought that the total losses were on this line together with the 100% load, and that's it, and you didn't mention that the transformer will be used for an extra harmonic switch environmental, the transformer will get that red area as additional losses. But the cooling isn't made for that one. So it will mean that you get a higher temperature as mentioned before, and probably in case you're running this transformer for many long time, you might have really some issues related to failures that you could have within the transformer. So please make sure that you, in case you know that the transformer is used in harmonics, make sure that you have mentioned it to the manufacturer so he can take that into account within the design of the transformer. This picture shows you the same situation. In this case, we have on the horizontal axis we have a loading of a transformer, and on the vertical axis we have mentioned the total loss of the transformer. This is a transformer of an 1 MVA transformer, and we are going to load it one time with and without a 6-pulse harmonic loading. If you don't have any harmonics, I've added a figure for an oil transformer which is in this scale, and also for a dry transformer. Normally a dry transformer has a little bit higher losses compared to an oil transformer. And if you then load it with harmonics, you will immediately see that the harmonic losses are the losses in total are much higher compared to the normal situation. In this case, in total, well, you would say normally with 100% without any loading, it will be about 10,000 watts of loss, and in case you have it with harmonic loss, it will be about, well, let's say 30,000 watts. So that's 3,000 watts, almost 1/3 that you get added as additional loading when you load the transformer for 100%. If you look at the other way, perhaps some people have asked me, okay, well, in case I know I have a 100% loaded transformer, I know that it has harmonics, why can I say, okay, I will take the amount of losses which I have at 100%, and looking back, what could be my maximum loading of the transformer in case I have harmonics, and then saying, okay, then I will add up to about, let's say, just above 80% of loading. And then I said to the people, no, you can't do it that way, because as mentioned before, harmonics or loading losses due to harmonics are not evenly distributed within a winding. So probably if you have a loading of 100%, you cannot say I can load it with 80% including harmonics, because still the temperature at certain spots in the winding are still too high, or can be too high. Then I would like to show you the demonstration of the transformer tool that we have made together with the APQI. We have developed a tool which can calculate for you the losses of a transformer, and also considering all kind of CO2 emissions. The tool is available for you. You can download it, and there is also a tool manual within the tool explaining all the backgrounds that we have. I hope you can see my tooling at this moment. I'm opening the tool at this moment, and you will see when you open the tool that there is a first slide explaining a little bit what you are expecting to do. Feel free to read it, but as I want to show you the tool, I would like to go to some slides and tell you what the tool is doing. This is actually a tool. This is not a PowerPoint presentation. I'm right now in the executing of this tool. When you start the tool and you press the Start and OK button, you will see on the above that there are some topics which you can identify. And I think when you start the tool, start with the help function. The help function will give you a kind of user manual. And if you open later on the user manual, it's a Word document. It will show you all the details that you need for this to run this tool. Agenda of this one. The table of contents, it's showing you how to start with this page and do the calculation, and also the results, how you can manage several databases within this tool, and also what kind of things, how it is calculated, and those kind of things. If you go to the next slide, within the tool, there is a language button. In case you want to select another language, we can do it in Chinese, Spanish, or Portuguese. I think most of you will probably select the English one. Also, in case you have other currencies than dollars or euros, you can select some of the different type of currency, and also it's possible to use folders, which is showing you later on results of calculations, and also some databases which can be adjusted by yourself. If we go to the tool, the first thing that you have to do is, and it's right mentioned, you have 4 steps which you should do within the tool. And the first step is also adding some economic data of a transformer. The first thing we would like to know from you, if you want to do a calculation for a couple of years, what is your economical lifetime expectation? And in this example, I've taken 25 years. The next step is that we would like to know what is your electricity price that you are using, and also your interest rate. And I think 7% is nowadays perhaps a little bit high on our side, but still, let's assume this is correct, then we can use those data. Another way which you very often see is that manufacturers are asking for a load evaluation value and a no load loss evaluation value. Very often you will see that that you have to fill in kind of a slide which is called an A and a B factor, and A is making a kind of evaluation for your no load losses, and B is an evaluation of the load losses. Within the manual we have explained everything. So feel free to read the manual, then you know exactly what A and B will be and how to use them the next time. Also CO2 emission data. Some countries they are asking that you have to take into account your CO2 emission. We have made a kind of library for several countries where you can immediately see what kind of pollution you will have per country. Do know this is based on situations from a couple of years ago, but later on I will show you how you can adjust those values for your own purpose. But there is a library within it which can be used. If we go back, then we have the selection of transformers, number 3. There we have made the distinction between distribution transformers and large power transformers. That's because the distribution transformers are very often transformers that are already manufactured, and while large power transformers are often customer-based transformers. If you would like to select some transformers, feel free to press the button distribution transformer, and we already added some of the transformers within this one in this database. The database is showing you can give the transformer a name, you can put in the type of transformers, it's a liquid or dry transformers or whatever you want to. You can add in the rated power, the related loss and no load loss, cooling losses in case you have them, for in case you have fans or those kind of things, feel free to add them. You can also add the winding eddy currents and then construction currents, etc. And you can as many as you want to, you can add them in this profile. And I've already selected some transformers which I would like to discuss with you. So I'm now using those transformers, including the financial figures, which are also given for those kind of transformers in these slides. So we will use those transformers in this example. The last one, once you have selected your transformers, of course you need to make sure that that you have a kind of that you know the transformer, how is it going to be loaded. In this example, you can mention as many much as periods if you want. We are looking at 1 year, so that means 8,760 hours. And you can make a lot of periods if you want to. In this example, I've shown you 3. I said, okay, this transformer is used during daylight for a couple of hours per year, during night and during the weekends, then it's a little bit less loaded or whatever. You can fill in the number of hours that you would like to have it, and also you can have the loading of the transformer as long as it's not larger the loading than the rating which you have given in section 3. Also, in case you want to use the power factor, feel free to adapt. And also you will see later on that there is a possibility to add harmonics or non-harmonics. And that's something I would like to demonstrate to you. There is also a button on which you can select if you have for that period harmonics or non-harmonics. It's very easy in case we have a transformer loaded with no harmonics. Then simply press the no harmonic and go back to the situation. Do it as well for the second, the night things. Go back, then you have selected no harmonics, and also for the weekends no harmonics. In this case, I've added some time economical data. I have added some CO2 emission. I've added some cost of CO2 in case we are going to produce. Sometimes within countries you have to pay an amount of value for each CO2 that you produce. Also, we have a selection of, in this case, 4 types of transformers, which we are going to look at. All have different purchase price, but all have different losses within the transformer. And now we are going to look what will happen in case we have this loading profile, which we just entered. Then I need to do a run. If I go to the run button on the left upper side and I press the button calculate, then it's going to do a calculation for me right now, and it's also immediately opening a folder which is showing me a Word document giving the results, and that's easy. I can open this document. And there you will see a standardized reporting, which you may adapt as whatever you want to do with it. In this case, it shows you the 4 transformers that we have selected, all the input data, and there you can see that, for instance, transformer 2 has a lower rated no load loss compared to the other transformers. You can also identify that transformer 4 has a lower load loss rating. The purchase price is mentioned over there. You will see that transformer 4 is the highest value and transformer 1 has the lowest value. You can add all kind of additional things what you would like to do, like costing sulfate cost if the transformer, if you get some money back from subsidized whatever. Based on the loading we have provided, the transformer is just calculating the total amount of losses we have. In this case, it's showing the annual losses for the no load, for the load, and also for the extra losses we have, and then count them all together. So in this situation, you will see that transformer 2 has the lowest losses. And it also calculates based on the price you have added, the amount of money that you spent on it. In case you also have CO2 emission, you can also calculate the number of CO2 emission which you are using for the transformer. So in this case, transformer 2 uses 29 tons per year. And also the capitalized costs, which is interesting, of course. That's the same as we discussed with the car. It's calculating the no load losses, the amount of money, and also the load losses and the extra losses in total which you have. Then it's giving you a kind of payback period referred to the reference. In this case, transformer number 1 is the reference. And I already told you in case we have, you don't know, an A and a B, which is calculated with a set. That's the evaluation for the loss and the no load loss. In case you don't know that figures, this tool will calculate them for you as well. So in this case, it's about $10 per watt for the no load losses, and for the load loss is about $3 per watt. This is just the corresponding input what we have provided to the transformer. That's the next slide. So you can always find out what kind of inputs you have had. And the last slide is showing you some figures. The capitalized costs of the transformer is the above one, and the figure below is the total energy losses. And in this case, you will see that transformer 2 is the most economic transformer during the lifetime, despite the fact that it was more expensive than transformer number 1. What I would like to ask you is to take into account the values of the total extra losses which we calculated in this situation. I've added them over there, and I would like to show you what the impact is in case we're adding some harmonics to the transformer. And if we go back to the transformer tool, in this transformer tool we said, okay, well, we haven't added any harmonic loading to the transformer, but of course we can select in case we have a harmonic loading on the transformer and see what the impact will be of the transformer. I go back to this one and I said, okay, let's assume that we have a 6-pulse transformer, so meaning we have a lot of 5th and 7th harmonics within the current. I will do it for each period, of course. Select the 6-pulse, and also for the last one select the 6-pulse. So now I've made a transformer, the same transformer as before. The transformer before didn't have any harmonic loading, and now I've added a harmonic loading of a 6-pulse transformer. If we run it again, this transformer, it will show me immediately the results that I got. The results are now given in this situation, and there I have the same output. It's still a Word document, but now we can have a look at the extra losses we have in total, which is caused by the harmonics. In the situation over here for transformers, you will see that transformer 1, let's remember that one, we have about 10,000 kilowatt hours per year, a little bit more in total as extra losses. That's this value. So if we go back to the other ones where we didn't have any harmonic loading, it was reduced to 2,700. So you can see immediately the impact in case you have a very high harmonic loading. In this case, it's almost 3 or 4 times higher, the extra losses. So that's the reason why I already said to you, try to when you're ordering a transformer and you know it will be heavy loaded with harmonics, make sure that you already mention it, because if you see that the extra losses are only calculated the cooling for, in this case, for 2,700 kilowatt hours a year, and then it's suddenly popping up due to harmonics, it's raised till 10,000. That's a huge impact. The last thing I would like to show you from this tool, and then I would love to invite you to use the tool as much as possible, is the editing part. The editing part is right on the above as well. It's a tab which you can use. Sorry, that's a save part. The folder part I would like to show you. And there you can also access the results. Then you get in the same folder as we have seen before. But you can also change databases which are within this tool. And if we go to the databases which are within this tool and we select that button, then you will see that there are 4 databases which you can adjust the way you would like to do it. The first one is a database with CO2 emission data. The next one is the harmonics content, and the last one is the transformer list which you can use. We already gave you some figures for the transformers, but if we open that one, for instance with Excel, there you will see the right same structure as you have within the tool, but I think in Excel it's more easily to adjust or to to delete transformers or to add transformers just the way you would like to do it, then press the save button within Excel and keep the name the same as you did it, and then you already can build up your own database. That's the same for the harmonic content. We have added some 3 profiles of harmonics, but in case you have your own harmonic profile, feel free to add it as well in the tool. And in case you also have another CO2 emission, feel free to add it in the tool. Basically, that's my demonstration of the tool. And as I mentioned before, in case you are going to use the tool, please go first to the help desk, help button, and read the manual, because it's a very sophisticated tool. Then I would like to go back to my presentation and my final slide. Conclusions. I think the transformer tool that we showed you today, the demonstration, you can use those tools for do your own evaluation if you, in case you have multiple transformers all with different kind of losses. You can calculate your own total cost of harmonics of ownership during a lifetime. The tool can also help you to see the impact of harmonics in the transformer, and also see the additional losses that you get due to harmonics. And the tool can also provide you all kinds of scenarios. Feel free to use as much as loading profiles as you would like to do. It's an unlimited number, so feel free to use it. And the last question, I think Manas also added that as well. In case you are using the tool, we would be very happy to get some feedback from you about the tool. Where can we improve it? Are you using it? For what circumstances are you using it? And those kind of things. So we can update it later on in case you are really interested in using this tool. That's from my point of view. I would like to share with you within this presentation. And in case, I think we will now address a Q&A session. Feel free to ask your questions, and in case we can't answer them right now, then we will do it later on.
Yes, dear participants, now that the expert has shared how to use the tool and explained the utility of the tool, if you have any questions, please put it into the chat box and we'll put it to the speaker for appropriately answering. Well, Mr. Walter, there is a question. Can you explain how to change A and B factors for loss capitalization?
Yes, I can. Let me go back to the transformer tool. Am I still in presentation mode or not?
Yes, you can.
Good. Within the economic data, there it's possible to add an A and a B factor, and A and B are normally used for the loading profile. If a transformer manufacturer has to make a design of a transformer, he will definitely choose the transformer which has the lowest cost price. And that will probably be a transformer with high losses because he is saving material. As explained before, and a transformer with a low purchase price is not often the best transformer from an economical perspective during the lifetime. So to make sure that a transformer manufacturer knows how you evaluate your losses during the lifetime, you can give him a kind of A and B factor. And A is telling you A is telling you the evaluation for the no load losses, and B is telling you the evaluation for the load losses. And those depends on the electricity price, the number of years, your interest rate that you are using. In case they can be calculated within this tool. So in case you have a transformer and you don't know what your A and B factor will be, and the manufacturer is asking for it, and he will often do, because in his formula he will calculate the total price of the transformer, including the capex and opex. He will calculate it during the design, taking into account and make the sum of the purchase price, add A times the no load losses plus B times the load losses, and the lowest values from that formula is the one that he is using to give you the transformer with the optimized losses for your case. But you have to provide him with the A and the B factor. In case you don't do it, he will definitely choose a transformer with very high losses, because he will saving a lot of material in it. This program can calculate it for you, so in case you don't know it, feel free to play. In case you know your economical lifetime, you know your energy price, you know your interest, and also you know your loading profile, add it within this tool and try to play with it, because it's independent from the losses that the transformer manufacturer later on will provide to you. And within the results slide, the Word document I showed you below, there is already mentioned the A and B factor, which you can use within your request to a transformer manufacturer. I hope this answered the question.
Oh, yeah, that's basically what we are understanding, that one can play around depending on the information at his disposal. Otherwise, you have already created a solid database to choose the A and B depending on the circumstances in which he is in. So
that's indeed correct. Yeah.
So I think we all have the responsibility to play around this tool, because it is an open access tool, and then give the feedback if something very unusual crops up. Another thing, Walter, this is a very nice compliment, and thank you for that compliment. The gentleman has mentioned. Let me say one thing. This is one of the simplest and best tool I have seen for impact of harmonics on transformer. I have a couple of questions. Are the losses considered based on current harmonics and voltage harmonics, or only current harmonics? So that is the first part of the question. And the second part, I understand it is current harmonics.
So I couldn't get the second question. Can you repeat that one again? Hello, this is Walter speaking. Could you repeat, please, again the second question? Otherwise, I will tell you about the first question. Thanks for the compliment. That's indeed, and we try to make a very easy software tool, because there are much complicated tools, and then I think you normally have to be a transformer design engineer before you understand those tooling, and that's not the tooling which we would like to provide to you as a user of transformer. Related to your question, did we take into account voltage harmonics or current harmonics? We only took into account the harmonics which are caused by loading, so in this case only the current harmonics. The voltage harmonics, that's something which you also see within transformers, but that's because the transformer itself is a non-linear loading due to the core. Voltage harmonics have not been taken into account in this transformer tool. That could perhaps be an expansion later on, but then you already get a more sophisticated tooling. And from my point of view, the voltage harmonic content will not have such a high impact on the total losses compared to the harmonics in loading that you have.
Okay, just to add, essentially, the voltage harmonics probably will impact the hysteresis and eddy current loss, which in any case minuscule percentage of the total loss. So the impact of voltage harmonics probably will not be so heavy when we are considering for our day-to-day use of this tool, and the current harmonic consideration currently what has been taken should serve our purpose as a basic user rather than becoming a complicated designer experience. It is from application point of view. It's a very useful and easy to use tool for us. Thank you, Mr. Walter,
You're welcome.
for your contribution. Okay, then uh, we uh, we have another question. How K factor affects harmonic losses in transformers?
Ah, excellent question. The K factor, which is I think more used in the US than within Europe. In the US, they have another way of dealing with harmonics and specification of transformers. We didn't look within this presentation on the K factor, but in case someone is interested, in the past we have made a report on that, including all the theoretical background, which is also used in this tooling. So I will be happy to provide that report to you. As a matter of fact, I think it's also used on the Leonardo Energy website and free for download as well. And there we are explaining all kind of different situations within the US compared to what we use in the other part of the world. And also the K factor is mentioned over there.
Okay. So the next question is, what should be the vector group for mitigation of harmonics?
That's a really tricky question. Normally, when you want to mitigate harmonic loading and transformers, you will very often see that third and multiples of the third harmonics, which are added to a loading, and in case you have a delta winding, will be compensated within a transformer. Be careful. When I say compensated, it means that you will still have that harmonic within the windings of the transformer. So it will still heat up your transformer winding. While you don't see it on the outside of the transformer, only on one side where you added those harmonics. If you are talking about fifth, seventh, and higher harmonic currents, you will also see that in case, for instance, like you have two transformers, a YY and a Y delta, can be used to compensate fifth or seventh harmonics. So then you get a kind of harmonic bridge with 12 pulse harmonics. And in case you, that's not enough, in case you still have a lot of harmonics content in your loading, you can also use zigzag windings, so the Z windings in case you want them. But do know those will be expensive transformers and will be definitely special transformers. So then you are playing with the angle around. So there are possibilities to use transformers to reduce your harmonic content. But still the harmonic content will flow within some parts of the winding of the transformer. So make sure that you still add those values as well when you specify the transformer. But there are possibilities to reduce it. I think we have done it in some industries, and also with traction for the trains. You will see them very often used over there to reduce the harmonics outside of the loading of those equipment.
Thank you. And before we move to the next question, my compliment to the person who has posed this question, simply because he is mentioning, I'm already using this tool, and can we add the harmonics manually? So we must compliment you that you have taken the initiative to use the tool. Uh, so you have a question there, can you add the harmonics manually?
He means can adjust the harmonics manually
Yeah.
in the tool. Yeah, that's possible. I don't know if I'm still on the screen, but if you go to the tab folder, there we have a tab databases, and if you go to the databases, there is also a file containing harmonic totals. You can open that file with Excel or with Notepad. And so in this case, you will see on the above, you will see the spectrum, the first, third, 5, second, and etc. harmonics. And also you can add, in case you have measured your own harmonics content, you can add them as a profile. You can make your own profile over here and add those to one. Remember one thing, you also must add the 50 Hertz or 60 Hertz, whatever you are living on, and mention that one as 100%. And
Yeah,
you
that is
must fill in,
fundamental.
that's the fundamental, yeah, that must be 100% in this tooling. But it's possible to adjust your own harmonic spectrum. Feel free to do it.
Great. So we move to the next question. What should be the vector group for 11th and 13th harmonic?
So the 12 pulse. Then what I said before, you can use two transformers, Y or Y delta. And then I think the one should be in, well, it doesn't matter how you calculate it, but both of those transformers, or you can add one transformer with a YY delta configuration. So make it 3 winding transformers. But very often you will see that people buy two transformers having the same output, but the only one is in YY and the other one is in Y delta. And then you can compensate the 5th and 6th harmonics, so you're getting only the 11 and 30 harmonics. In case you want to reduce your 11 and 30 harmonics, then you need to go to a kind of configuration on which you use transformers. It could be YY and Y delta, but then you need them 2 times, and then make sure that you have a phase shift in between them. Which I think it's 180 degrees difference, if I remember it right. So then you can compensate the 11 and 30 harmonics. If you want to do higher harmonics, then you will get up to an zigzag windings, which is, so told before, very expensive.
Okay, we have number of other questions, but I think we'll stop at this question, and all other questions we will be responding through a tabulated question answer FAQ format, which will be hosted in the website in couple of days. So the last question for today, we are constrained for paucity of time. It is, what is the ratio of losses of current harmonic losses and voltage harmonics losses?
Can you repeat that question again? What is the
What is the ratio of losses of current harmonic losses and voltage harmonic losses?
in this? Okay, for transformers you mean?
Yeah, I think this question is not very clear because we are considering that current harmonics and voltage harmonics are of a constant magnitude, and then we will consider the loss out of that and do the proportion to bring out the ratio. It is not the
Yeah.
case in practical application. The current harmonics which the transformer is catering to may vary depending on what node it is catering. So there can be enormous variation. As far as voltage harmonics is concerned, there may not be any voltage harmonics, or there may be voltage harmonics which is inherent and which will be very low magnitude. So we really regret that there is no specific answer to this question. So with that, I think we would. Okay, there is. I think I will take another question because we have another 1.5 minutes with us. What is the impedance of transformer and its impact on harmonics? Currently, I came across two 2 MVA transformer, one with 6.25% and other with 9.05% percentage impedance.
In general, you can say, but it's very generic, that the higher the impedance will be, the higher the additional losses will be in the transformer. So you can imagine if you have two transformers with a kind of same loading and the same rating, that the transformer with the high impedance normally will also have higher extra losses within the transformer. So if you know that the extra losses are also important for the harmonic losses, you can imagine that the transformer with a higher impedance normally has also a lower impact, has a lower impact, higher losses. So we compared for the harmonics. But it depends a little bit on the design. But I said it's just a generic answer what I can provide. We can also imagine that in case someone is making a transformer with a high impedance and he's still using CTC wires compared to a transformer with a lower impedance but using just a single wire, then it definitely will make a huge impact on the harmonics for the transformer with the low impedance, because the eddy currents will be higher in that situation. But if they use the same material and the same kind of winding arrangement, then normally the transformer with a high impedance has higher losses, additional losses, sorry.
Okay. So thank you, Walter, for those answers. I take this occasion on behalf of the APQI community and all the attendees to express our sincere gratitude and thanks to our expert speaker, Mr. Walter Hirshhorst, for today. And with that, we bring this session to the close, and please be on touch for this tool improvement with your feedback, and also visit apqi.org at points of time to look for some new tools into the power quality area to help in our day-to-day job. With that, I thank you once again, each one of you, for participating, sparing your time, and wish you a very good evening and a very good afternoon. Bye for now. Thank you.